Hello and welcome to the fourth lecture in our natural disasters course. In this lecture we'll be discussing plate tectonics and earthquakes. So we mentioned that the Earth's outer layer, the lithosphere, is broken into pieces known as tectonic plates, and that those plates interact with each other along their boundaries. One of the manifestations of those interactions are earthquakes. It's not to say that all earthquakes occur at plate boundaries, but most earthquakes occur at plate boundaries. It's mostly due to the stresses we talked about in the last lecture due to plate motion are most substantial at the plate boundaries, along the plate boundaries. So we can look at a map of Earth and where the plate boundaries are mapped out, as you can see here. The black arrows indicate the directions of the plate motions. And then if we switch and look at the same map of the planet, but instead of mapping the plate boundaries explicitly, we map the locations of earthquakes, which are the red dots. And we can see that they do a fairly good job of mapping out those plate boundaries. We can go back and forth here to see. And so this activity, the seismic activity, is concentrated, not exclusively at plate boundaries, but concentrated at plate boundaries. And we do have earthquakes, as you can see, those red dots that are not along plate boundaries. Those are called intra-plate earthquakes, but most earthquakes occur along plate boundaries. And so in this lecture, we're going to look at what type of earthquakes occur along which type of plate boundaries. So first we have this idealized plate. So this is just a theoretical plate. It's moving in the direction of this red arrow. And so since it's moving this way, my pen is activated, it's going to be diverging from a plate on this end, converging with a plate on this end, and sliding along a plate on these ends. So as a result, we will have a divergent plate boundary over here, a convergent plate boundary over here, and two transform plate boundaries on the sides. So divergent plate boundaries, as we mentioned, is where the plates move away from each other, or pulled away from each other. And so due to the moving away, they are under tensional stress. And if the rock has just formed at these divergent plate boundaries, these spreading centers, volcanism occurs at these, they're called mid-ocean ridges, these divergent plate boundaries in the seafloor. And as the plates move away, molten rock erupts to the surface and it solidifies, forming new rock at the surface. Because if that didn't happen, a gap would develop as the plates move away from each other. So the rock is young, it just formed, it's fairly warm, and it's being pulled apart. And so because it's warm and just formed, it's fairly weak. And so it fails with minimal stress compared to other rock. And so that, as a result, it doesn't allow for a large amount of energy to accumulate in rock before it fails. And so we saw in our last lecture that the size of the earthquake is proportional to the amount of energy that's able to be stored in the rock through the elastic deformation of the rock before it is able to return to its original shape during rupture. And since there's no significant strain or accumulation of energy, it results in small earthquakes. And if they're small, remember, they're frequent. So frequent small earthquakes. And because this region is under tensional stress, remember from last lecture, we will have a type of dip slip faulting known as normal faulting. So we have tensional or extensional forces result in normal faulting, where the foot wall slides up, the hanging wall slides down. And you can see normal faulting often results in the formation of a valley. So it's being pulled apart. So this is a divergent plate boundary under land. So this is a continent. The plate's being pulled, the lithosphere is being pulled apart. What happens is it begins to fracture, and normal fault, where the foot wall slides up, the hanging wall slides down, and it creates this valley. So we could see this happening, for example, in Iceland. So Iceland is an island in the northern Atlantic Ocean, and it happens to be half on the North American plate and half on the Eurasian plate. So this is a divergent plate boundary. And it's also a hot spot, which we haven't talked about, but it's elevated volcanism due to a small upwelling in the mantle. But anyways, that volcanism is creating the island. But as the island is created, the divergence is pulling the island apart. So this island is moving this way, this island is moving this way. So all this rock is under tensional stress. And you can see this is a normal fault right here, where this has slid up and this part has slid down. And the same thing on this side, this has slid up and this part has slid down. So you can see the actual divergent plate boundary running through the island. And so they have earthquakes here every time this slips, but they are not very large, relatively speaking. Also, we have in Eastern Africa, we have several divergent plate boundaries. So these are 3 divergent plate boundaries that come together right here. And I said that whenever divergent plate boundaries form under land, they create valleys. Well, these 2 valleys have since flooded, forming the Gulf of Aden and the Red Sea, where this is the East African Rift Valley, so it hasn't yet flooded. But there are several normal faults in here, and we have earthquakes that occur in this region. Not extremely large earthquakes. You can have large earthquakes, but not the extremely large ones like the 7.5 and above. And those are all due to the result of normal faulting. Another location on the planet we have in western Mexico, we have the Baja California Peninsula, was originally part of the rest of Mexico, but this divergent plate boundary is spreading, and it's kind of causing this part of Mexico to peel off of the rest, forming the Gulf of California. But this divergent plate boundary, the pulling apart of the rock under tensional stress causes normal faulting to occur. So we have some small frequent earthquakes here. So in summary of divergent plate boundaries, we have very many frequent earthquakes, but they're small. And they're small mainly because the tensional stress is in relatively young rock that isn't very strong, and so it cannot store a lot of energy before breaking or slipping. And therefore, the inability to store large amounts of energy results in smaller earthquakes. The next type of plate boundary we're going to look at are convergent plate boundaries. Unlike divergent plate boundaries, convergent plate boundaries are where the plates collide with each other. And you can imagine there is a massive amount of deformation in these plate boundaries. So the rock is significantly deforming, and so large amounts of energy are stored in these collisions of tectonic plates. And so whenever these large amounts of energy that are stored are released, they result in very large earthquakes. In fact, the largest earthquakes on the planet occur at convergent plate boundaries. So at convergent plate boundaries, we have tectonic plates colliding, and the region is under compressional stress, and it results in reverse faulting, where the footwall slides down and the hanging wall slides up. In this table, we see a list of the largest earthquakes through the time period of 1904 to 2011. We have the rank on the far left-hand column, location, moving right, and then year, the moment magnitude, and the cause. And you can see a subduction is where oceanic lithosphere converges with another plate and it sinks down into the Earth's mantle. So it's a convergent plate boundary. And you can see all of them except one, which is still a convergent. It's a continental convergent plate boundary. All of them are subduction. So all of these are a type of convergent plate boundary. All of these largest earthquakes that have occurred on the planet. You can see the largest earthquake ever recorded was in 1960, magnitude 9.5 off the coast of Chile. So here you can see an illustration of a subduction zone. So we have this plate moving this way, this plate moving this way. Oceanic lithosphere, the lithosphere is very thin and it sinks under the plate it's colliding with. And so you can see that process of subduction here. And so earthquakes, so the rock is being deformed and under stress and deforming all throughout this convergence area. So we have earthquakes occurring all through the area. Even in the lithosphere, as it subducts, earthquakes are occurring in the rock as it breaks and fractures. But the largest earthquakes occur along the interface, the fault right here. So as this is moving, subducting, this plate and this plate, they're stuck together along this fault due to friction. And so over time, what happens is this rock will bend upward and this rock will be pulled down. And so it's almost flexed, kind of like the end of a diving board. I'm exaggerating here. And then whenever the fault slips, this slides up and this slides down as it returns to its original shape. And so that large amount of energy is released as it slips back up. So we could see that process in this animation here, where we have this plate subducting, this oceanic plate subducting, in this case, under a continental plate. Here is the actual plate boundary along the surface, and then here is the fault. See, as they converge, it's locked together in this yellow zone by friction. So as a result, this overriding plate begins to deform. Now, as it deforms, elastic potential energy is being stored in it. It's like a spring being pushed back. And eventually, there's not enough friction to hold this fault together, and so it slips, and all that stored energy is released. So seismologists use what is known as the seismic gap method to assess at least partly assess the risk of earthquakes along faults. This can be done along subduction zones and transform plate boundaries, as we'll look at later. But how this works is, we know that in order for a large earthquake to occur, large amounts of strain, large amounts of deformation have had to accumulate along the fault. So we need a large amount of energy to be stored. So this large amount of energy needs to be stored in order for a large earthquake to occur whenever the energy is released. So the idea is if a segment of the fault has ruptured in the recent past, then that energy has been released, and therefore there cannot be a large amount of energy built up along that segment of the fault, and therefore that segment of the fault does not pose a significant risk for a large earthquake. So what they do is they look at faults and they map out segments of the fault that have ruptured and when they have ruptured. So that's what we see in this figure here. The brown shaded regions are areas of the fault that have ruptured, and in the number next to it is the year in which that rupture occurred. And so let's say, for example, let's find one of the most recent ones, 1964, right here, 1965, this ruptured. So this ruptured, several decades ago, right? So it's like 40, 50, 60 some years ago. And so the chances of a large earthquake occurring here anytime soon are relatively small. We can never say non-existent, but we can say they're relatively small. Where would the largest near-term risk exist? Well, it's in the segments of the fault that haven't ruptured in recent history. So areas like this, these are called seismic gaps. That's why it's called the seismic gap method. There are gaps in the fault that have not experienced any seismicity. where the energy has not been released. And so those are like a slingshot where the rubber band is pulled back all the way and it could slip at any moment. And so those are the greatest hazard. Now, this figure was made pre-2011, but in 2011 we had the Tohoku earthquake that triggered the tsunami as well, and it filled in that gap right there. Actually, it didn't fill in the entire gap, it filled in mostly the northern half of the gap. Tokyo is right there. There's still a gap right next to Tokyo. But so that large earthquake occurring there was not a big surprise because that was a seismic gap. Here, looking at another fault, this is the Indonesian subduction zone. This is where the Indian Australian plate is colliding and subducting under the Sunda plate. This is the plate boundary right here. Prior to 2004, I should say that the regions of the fault that have ruptured are shaded with different colors, either purple or green. Prior to 2004, only the purple shaded regions had ruptured within recorded history. And we're going back into the 1860s in some of these, even in the late 1700s. So this ruptured in the late 1700s. And so prior to 2004, besides these two purple spots right here, this whole segment of the fault had not ruptured. And so that was a very large gap. And that had, give seismologists some significant alarm. This is a large hazard to this region, this large gap. It hasn't ruptured in hundreds of years, and it is primed to rupture. Now, best case scenario is a small segment of it ruptures. And then several years later, another small segment ruptures. Then several years later, another small segment ruptures. And then several years later, another small segment ruptures. So it ruptures piecewise, right? So all that energy would not be released at once. It released over the course of several years in several discrete, instances, large earthquakes with, aftershocks occurring after it. Unfortunately, the worst case scenario happened where the rupture started down here and this whole segment ruptured at once. And because it was a very long segment of the fault that ruptured, there was a large amount of energy that was released. And this is one of the top 3 largest earthquakes in recorded history. This 2004, it's called the Sumatra Andaman earthquake. This earthquake is the one that triggered the tsunami in the Indian Ocean that was responsible for almost 250,000 deaths. So one of the most lethal natural disasters in human history, partly due to the size of the event, right? Such a large earthquake and tsunami, but also partly due to all those human factors, right? The high population density of the Southeastern Asian region, and the countries ranking low on democracy index and GDP levels. So it was the worst case scenario. And then one more example, this is a convergent plate boundary. So the Cocos plate subducts under the North American plate on the west coast of Mexico. All right, so in 1985, there was a large earthquake. So prior to 1985, this had ruptured, this had ruptured, this had ruptured, and this had ruptured. So three, or I should say, several notable gaps existed. This gap, and this gap. In 1985, this gap known as the Michoacan gap, it ruptured. And it resulted as a large segment of the fault that ruptured, an 8.1 magnitude earthquake with 7.5 and 7.3 aftershocks. You can see here this 21st of September 1985 came 2 days later. That was an aftershock. The earthquake was 350 kilometers away from Mexico City over here, but there was intense damage. At least 8,000 people were killed by building collapses. And so this earthquake was expected, right? Because seismologists knew that these gaps existed, and they knew it was just a matter of time before they ruptured, right? And so just like this one, this gap still exists right here. It's just a matter of time before it ruptures. So the question is did we learn from the 1985 event? Because we have this event looming in the future. So did we learn from this event? And did the people of Mexico rebuild in a way to mitigate this future event? No, that is the question. So what did we learn from the 1985 Mexico City earthquake? Well, we learned what I mentioned in our last lecture is that the earthquakes don't kill people. It's the failure of infrastructure that kills people. 5,700 buildings of Mexico City were damaged, while small towns along the coast, much closer to the actual epicenter of the earthquake, were relatively unscathed. So the difference is that Mexico City is built on a dried up lake bed, which has a bunch of sediments. We're at the bottom of that lake, so it's built on soft sediments, which amplify the vibrations, where the pueblos built on the mountains along the coast were on bedrock, which we know from last lecture minimizes the vibrations. So this is the seismogram from recorded on the hard rocks near the coast, where the green is the seismogram recorded on the soft muds near Mexico City. So you can see how those soft sediments amplified the shaking. And so not only were the sediments amplifying the shaking within the basin that Mexico City was built in, but the buildings were not built properly to handle the shaking. So resonance occurred between the seismic waves, the soft lake sediment foundations, and the improperly designed buildings, all of them vibrating most intensely at about 1 to 2 second periods, and destroyed many buildings. So buildings were split down the middle. Buildings that were had an L shape, one was shaked at one period, the other shaked at a different period, causing them to break. Buildings that had different heights, obviously this shakes at a certain period, higher frequency, lower period. This shakes at a larger period, lower frequency, and so they would break along there. And then two buildings at different heights that are next to each other would shake at different frequencies and bump into each other. So the buildings were not built to withstand shaking, especially the magnitude of shaking experienced, and there was large scale failure. So in the Pacific Northwest of the United States, most people think of California as a large seismic hazard, which it is, but there's others in the United States too, including the Pacific Northwest and a region known as the Cascadia Subduction Zone. So the Cascadia Subduction Zone is where the Juan de Fuca Plate collides with and subducts under North American Plate. And so there have been no major earthquakes in the Pacific Northwest in the last 200 years. So the idea of a large seismic hazard is almost non-existent within the public consciousness, widespread, unlike California, right? People think California, earthquakes. People don't necessarily associate Washington State, Oregon State with earthquakes. But there hasn't been large earthquakes in the last 200 years. Why is that? Has the subduction stopped? Well, no, there's still active volcanism, which as we'll learn later that volcanism results from subduction. And so, well, are the plates just sliding past each other smoothly? Maybe the rock isn't deforming. They know that's probably not the case, especially considering that this rock is so young here, because this is the divergent plate boundaries being formed. So young rock is warmer and it's a little stickier, so it's even more friction. So the fact that there hasn't been a large earthquake here in the last several hundred years is very concerning, because if you go back further, there have been several large earthquakes in prehistoric times, earlier than 1750.
so pre, European historic times. There has been there's oral histories of large earthquakes in the region in the indigenous populations. So we know that large earthquakes have occurred here in the past. Because of that, and because there hasn't been large earthquakes along this fault in the recent past, there are significant seismic gaps along this subduction zone, which is concerning. So it's not a question of if, it's a question of when large earthquake or earthquakes will occur. Now, this subduction setting is similar to Japan and Chile, which we know both have very large earthquakes. Japan's subduction zone relieved stress with 2 magnitude 8.1 earthquakes in 44 and 46, and recently again in 2011. For the Chilean subduction zone, as I mentioned earlier, had the world's largest earthquake ever measured in 1960 with a magnitude 9.5. And so that 1960 Chilean event would be comparable to an earthquake series in this Cascadia region due to inactivity and the amount of energy that must be stored on that fault. So could Cascadia have a magnitude 9 earthquake? Yes. The answer is definitively yes. It already has, and it will again. In the year 1700, there was a magnitude 9 earthquake in the Pacific Northwest. We know this because it triggered a change in the local sea level, not because the sea level changed, but because when the ground elastically rebound, the rock elastically rebound, it changed elevation and it caused flooding near the coast. And we can see that trees near the coast all died in the year 1700. So the trees, they were as they dropped in elevation and it flooded, those trees died, but in that low-lying water, the trees rotted very slowly because of the lack of oxygen. So they are preserved so they can look at the trees, exhume the trees, and look at the tree rings. And using dendrochronology, they can match when these trees lived with other trees that are still alive further inland. And they see that all these trees in this region died in the year 1699 when the large earthquake occurred. And also, Japan had a written record at this time, and they recorded a tsunami that came ashore. So there was no earthquake, no detectable earthquake in Japan. So the earthquake must have occurred far away. That triggered the tsunami that moved across the entire Pacific Ocean and hit the coasts of Japan in the year 1700. So, so the effects of a magnitude 9 earthquake would have 3 to 5 minutes of intense shaking, and it would likely trigger a tsunami 10 meters high, 15 to 40 minutes after the earthquake. So we have a very large hazard in the Pacific Northwest, seismic hazard that is. And so the question is what are people doing now to mitigate that event? And they do build buildings to seismic code now, and they are working to retrofit. They have evacuation plans in place for the coastal communities of Washington and Oregon in the event of the tsunami that the earthquake could trigger. So there are mitigation efforts in place. Let's just hope that they're enough. So other convergent zones, besides subduction, we have continental collision. This is whenever a continental sphere collides with other continental sphere, as is happening in India. Today, India has moved 2,000 kilometers to the north and has began to collide with Eurasia, and that collision is causing a large amount of deformation, resulting in the formation of the Himalaya Mountains. And because of all this deformation, there's large amounts of energy being stored and released, and therefore large earthquakes. So India continues to move north about 5 centimeters per year into Asia, and this is occurring along a 2,000 kilometer long front. And this deformation resulting from this collision is affecting India, Pakistan, Afghanistan, Tibet, the Tibetan Plateau, part of China, and well, it depends who you ask, and then Eastern Russia. So Mongolia and China, they've had great earthquakes as a result from this convergence. Some of the some of the most significant earthquakes in history have occurred in this region. So some case examples in 2008, 2005, and 2001, earthquakes in China, Pakistan, and India caused by this collision. So May 2008, there was an earthquake in the Sichuan province of China, killed 87,500 people. In 2005 in Kashmir, which is a part of, well, once again, depends on who you ask, Pakistan or India, it killed 88,000 people. January 2001, an earthquake in India killed more than 20,000 people. And so seismic gaps, such as a 600-kilometer long section in central Himalayas, they exist throughout the region. Remember, these seismic gaps are just locked and loaded segments of the fault that are ready to rupture. And the rapid population growth in the region, sporadic seismic safety codes, and poor construction practices are all a recipe for disaster. None of the recent earthquakes had a direct hit on major cities. That's been fortunate in the past. We can't assume that people will remain to be that fortunate moving forward. So going back even further, in 1556, the deadliest earthquake in history occurred where 830,000 people were killed. So at this time, there was very soft soil, and the people were digging into the hillsides, creating caves as homes. But when the earthquake occurred, the shaking caused the caves to collapse. And then in 1976, the deadliest earthquake in recent history, more than 240,000 people were killed. It was a dense mining city, 2 million. Most of the buildings built out of mud brick, masonry structure. Remember, masonry structures do not fare well with earthquakes. Built under lenient building codes, and 93% of residential buildings collapsed. Once again, it's not the earthquake that kills people, it's the failure of infrastructure that kills people. Another continental convergent plate boundary is the Arabian Plate moving and colliding with the Eurasian Plate. That's creating this convergence. And this is the convergent plate boundary that results in the earthquakes in the Iran region. In the last 48 years, there's been 10 earthquakes. It killed over 150,000 people in Iran. In December 2003, construction methods of mud brick walls and heavy roofs caused the collapse of homes to kill 41,000 people. So I always reiterate this, right? It's the earthquakes don't kill people. The collapse of buildings kill people. So finally, we have the third type of fault, which is transform plate boundaries. Most transform plate boundaries are small plate boundaries that connect segments of divergent plate boundaries along the floor, but there are a handful of larger segments of transform plate boundaries on continental crust, continental lithosphere. They're the most notorious. They exhibit relatively large earthquakes, not as large as convergent plate boundaries, but significantly larger than divergent plate boundaries. So one example is the Dead Sea Fault Zone. It runs through the Holy Land. It has steps in the fault, so there's small segments of divergence, and those divergence create little valleys, actually, which have created the Sea of Galilee, the Dead Sea, and so on. And so this generates magnitude 6 to 7 earthquakes about every 1 to 200 years. And then there's the transform plate boundary known as the San Andreas Fault, which most are probably familiar with. It runs from Northern California down the rest of California to the top of the Gulf of California. And so these shaded regions are segments of the fault that ruptured recently. So here's the Owens Valley earthquake at 1872. And then we had this rupture in 1857. And then in 1906, we had this large rupture, which was a large rupture that really shook San Francisco at the time. So in 1906, there was about 400,000 people living in San Francisco, right? It was not the size it is today. There was intense ground shaking early morning hours. The damage was much worse in areas constructed on artificial fill, loose, unconsolidated material, rather than consolidated rock or even more consolidated sediment. So there's going to see another theme. You build on loose ground, loose foundation that amplifies the shaking, increases the destruction. Many fires broke out and the water lines were destroyed, making firefighting impossible. the fire actually caused 10 times more damage than the shaking. Once again, that's the failure of the infrastructure. Moving forward in time, from almost 80 years later, a little more than 80 years later, we have the World Series earthquake, also known as the Loma Prieta earthquake in 1989. So it's called the World Series earthquake because it occurred just prior to the scheduled start of Game 3 of the World Series. The rupture, it was the rupture of the southernmost 42 kilometers of the segment of the fault that ruptured in 1906. It was deep, this rupture, so the area of the fault that ruptured was deep beneath the surface, and so there actually was not significant offset in the ground near the surface. And so rupture lasted only 7 seconds. It was short for relatively short for a magnitude 7 earthquake. As we said, the main shock was 7.0, but it had numerous aftershocks. The Loma Prieta region was a seismic gap in the San Andreas fault. So if we see this is the cross section of the fault. So this is the surface, and this is the fault plane. This rectangle, and all these black dots are earthquakes. And so where you see a lot of black dots, that's a lot of seismicity. That means that all the energy being stored here is being bled off, right? It's not allowed to accumulate. There's no large threat of earthquakes where there is big earthquakes where there's seismicity. But you see there was areas where there is relatively little seismicity, and those are the seismic gaps. And the Loma Prieta earthquake in 1989, this was the initial rupture. That was the large earthquake, and these are all aftershocks, but it filled in that gap. All right, are there other seismic gaps in the region? Yes, definitely. So just north and south of San Francisco, and then further south. And so when you talk about the next big one hitting San Francisco, you're referring to these seismic gaps. So the destruction in the 1989 earthquake was much less than it could have been, as the shaking only lasted 11 seconds. 67 people were killed. There's almost 4,000 injuries, and 12,000 people were homeless, and $6 billion in damage. Like we saw, very few people died, but very costly, right? As a result of it being in the United States, right, where we had buildings built to seismic code, we had the infrastructure built to, to mitigate the impacts, but as a result, there occurs a lot of damage because of the larger economy. So once again, this earthquake is an example of how earthquakes don't kill, buildings do. Near the epicenter, the damage was mostly due to older, poorly designed buildings. The seismic waves were amplified by the soft muds and artificial fill foundations around the San Francisco Bay. So the ground motion on the soft sediment sites was 10 times stronger than that in the nearby rocks. And then further from the epicenter, considerable damage was done to poorly sited and poorly designed structures, mainly the Marina District and Interstate 880. So in the Marina District, this was part of San Francisco that was built out into the bay. What they actually did is they used some of the rubble from the 1906 earthquake, and they dumped it into the bay to expand into the bay, and they built on it. And so that loose unconsolidated material amplified the shaking. And a lot of these buildings had soft first stories, or they had garages on the first floor. Because of limited space, they would put the garage on the first floor. And so a combination of those soft foundations, which amplify the shaking, and the soft first stories, relatively hollow first stories, caused damage. So, as I said, it was built on from the debris. This region that was developed, it was debris from the 1906 earthquake. It was used to fill in the bay to expand for development. It amplified the shaking, and also whenever loose unconsolidated material shakes, a process known as liquefaction can occur, where the sediment almost behaves as a liquid or a fluid, and it flows. So liquefaction occurred. Soft first stories, the ground floor of the buildings As I said, we're cleared out to make parking because of limited space, leaving the building without adequate support for the rest of the building. And so what happens is it pancakes down onto the first floor. And liquefaction, as I mentioned, is whenever the sediments are shaking, they must flow as a fluid. Here's an example of what can happen. These are apartment buildings in Indonesia. The shaking caused the soft sediment underneath them to liquefact, and it literally flowed out from underneath the foundation of the building, causing the buildings just to topple over. And this car actually sunk down into the sediments as it liquefacted during an earthquake. And then when the shaking stops, the sediment kind of reconsolidates, and the car is just stuck down to the sediment, which is very crazy. So we have those lessons we can learn from the Marina District, and then there's Interstate 880. 42 people were killed when the upper deck collapsed down onto the lower deck. And the reason 880 failed is the section that was built on these soft muds. So you can see this as bedrock, as a sand and gravel, and the lighter colored material is soft mud. And you can see seismograms from different regions and see how the shaking was most significant in the soft mud. And so it's the segment of Interstate 880 that was built in those soft muds that collapsed due to the amplified shaking. So either A, we cannot build there, or B, we build there, but we build our structures to be able to withstand the magnified shaking. And this could have been predicted because freeways collapsed in the 1971 San Fernando earthquake. And this is a YouTube video about the 1989 Loma Prieta earthquake. If you have time, it's worth watching. It's kind of through the eyes of the news media, which is interesting. But this concludes our lecture on earthquakes and plate tectonics. Thank you very much.